So online participants, can you hear me?
Yes.
Yes, perfect. So welcome everybody to this afternoon session. And it's my pleasure to introduce the first speaker, who is Alexandra Tzella from University of Birmingham. And she's going to talk about diffusion in arrays of obstacles beyond homogenisation.
Okay, so I think I'm probably going to be the only speaker without a flow here. I'm sorry. However, we do have obstacles, and obstacles do cause dispersion and mixing. Okay, right. So this is joint work with my PhD student who is finishing, and a colleague, Daniel Login, who is a numerical analyst and does all the finite-element simulations, and Jack Van Ness at the University of Edinburgh. Okay, so we're looking at dispersion and mixing in media with obstacles. Our media are going to be very simplified, but generally, this kind of problem is very important in many environmental engineering applications. For example, in the transport of contaminants in soils and aquifers, and the delivery of drug or the transport of nutrients in biological tissues. So these are usually quite random environments, but more ordered environments are such like filtration devices, where you have more ordered arrays of obstacles in there. And again, you're interested in the evolution of chemicals, tracers, dyes within these environments. And the challenge is great because you don't just have advection and diffusion, but you also have a complicated geometry, which poses problems to both theoreticians and numerical analysts, as well as for experimentalists, because it's not very easy to view the sort of situation inside, let's say, a porous medium inside the soil. It's very difficult to visualize it. Anyhow, there have been more techniques now that allow this in the last decade or so. Some recent results here by Susie and others show the evolution of a blob of dye inside isotropically random medium full of obstacles. And there is some flow here that is imposed by constant pressure difference. And of course, as the time evolves, the dye gets this spreads out, so disperses, and at the same time mixing, as evidenced by the highly heterogeneous sort of structure in the concentration field. And this is another experimental example. I'm not sure how they did that. That was much earlier on in the 2000s. But the difference here is that you have chemicals, and the chemicals are such that I think there is some kind of autocatalytic reaction. I'm not quite sure, but basically there is a front that is being generated and it spreads to cover the whole domain. This is at these pictures are at larger length scales. So sort of like a more macroscopic picture of the previous sort of figure I showed. And the question is, can we obtain a coarse-grained description of the evolution of the concentration and the chemicals in such media? Okay, so this is a very long-standing problem for the kind of stationary, random, or periodic media that we're interested in, there is a very standard sort of picture for the evolution of the concentration really suddenly inside the domain. And this is in terms of a Gaussian approximation resulting from an effective diffusion equation, which involves two parameters, an effective velocity, and which arises when you have some background flow, and an effective diffusivity tensor. And this kind of representation was first developed by Taylor and Harris in the 50s in the context of shear flows, and translated to the context of porous media by Brenner in the early 80s. And it actually underwent through the robust, it remained pretty robust once people started using more sophisticated methods rather than the sort of method of moments developed by these people. It sort of remained robust under homogenization theory, which sort of ended up with the same representation. And it's pretty good at capturing dispersion for distances small from the center of mass. So in other words, order t to the 1/2, where t is large. And this can be seen as a sort of, yes, okay, but it has limitations for distances larger than that. So these kind of limitations are sort of mirroring the limitation associated with the central limit theorem, that again tells you that it's only valid within a certain distance from the center of mass. Okay, so t to the 1/2. So one can do better with using large deviations. Better in what sense? If you want to capture the tails of the distributions, you want to go beyond the order t to the 1/2 distance from the center of mass. And in order to capture, let's say, the low concentrations that your PDF may have. And why do you want to do that? Well, maybe you have some radioactive nuclei that is in some kind of reservoir full of soil, let's say, or whatever, in some kind of nuclear plant. And you want to really be able to capture the low concentrations because they are highly toxic. Or I won't be able to speak about this much today, but you may also, it is also important to capture these tails if you want to describe the spread of reactions accurately in a complex medium like that. Okay, so what's this large deviations? Well, it assumes a more general form for the concentration that is in terms of an exponential function that depends on the rate function g, and g is going to be the key quantity in this talk. And this was first sort of employed in the context of advection diffusion and dispersion by Hens and Van Este in 2014. And what we're doing here is to adapt the approach to describe the situation in this media with obstacles. Okay, so it's a very basic problem. It's a very long-standing problem, a very large, wide literature on this thing. So we just have diffusions in the presence of impermeable, obstacles. And we look in particular at two situations: high porosity, or what we call dilute case, where the obstacles are small, and a low porosity, or what we call dense case, where the obstacles are big. And the aim is to obtain the macroscopic behavior of the concentration. So, as mentioned, many approaches have been employed ever since the 19th century. It's a very long-standing problem, and the most systematic one is that obtained from using homogenization theory, and that is like a standard example. When one teaches homogenization theory, probably one would start with something like that. Okay, so, and then you end up with an effective diffusion equation with an effective diffusivity, which can be explicitly obtained in the asymptotic limits of the dilute case, like over here, or on the dense case over here. So the dilute case was sort of tackled by Maxwell and Rayleigh, and Keller in the 60s attacked this more the dense case over here. Okay, so how does this effective diffusion come out? Usually the standard approach is to obtain the macroscopic behavior by taking the diffusive rescaling. In that way, x squared over t remains order 1 as delta goes to 0. And then homogenization theory sort of ensures that the concentration tends to the rescaled, to the concentration obtained with the rescaled parameters, where now this theta delta satisfies the diffusion equation. Again, of course, it's a diffusive rescaling, so there's no big alteration. It's just the position of the obstacles that change. And then what happens is one can employ the method of multiple scales, which has the advantage that it can be rigorously sort of verified, these kind of results. And what one sees is that you have like two scales. One that is the macro scale, that is sort of the scale over which the scalar sort of evolves at large times, and one that is the microscale, which is basically the what happens at the period within the cell obtained from the period of the background medium. And so you have the macroscale parameter here that lives in R2, in this case, which we are considering two-dimensional domains, and the microscale parameter y that lives in a domain that is obtained by taking away the obstacles from this position. So it's a multiply connected domain over which it lives. And because the large difference between the two scales, the usual thing is to then consider the microscale and the macroscale as independent and write the rescaled concentration in terms of x and y. And that affects the special derivatives and gives rise, and then the diffusion equation becomes something like that. And then the last step is to take a regular expansion in powers of delta to obtain an infinite number of problems that one can solve with a leading one determining usually the sort of the majority of the behavior. And of course, one thing I should say is that also that this y, which is the microscale parameter, the dependence of theta on y is such that theta is periodic on y. So basically, it inherits the background periodicity of the medium. Okay, so, oh yes, and the leading order problem is such that this term here turns out to be independent of the microscale, so it's just a homogeneous function. At the next order, we have a problem that is given here, and which can sort of, whose solution may be written in terms of the vector function gamma as annotated here, where gamma solves a cell problem. So it's a problem that is entirely defined on the cell omega, whose, in which case here we have taken the cell with a center to have the obstacle, but any cell could work out. You could choose it to be a bit different, as I will do actually in later part of the talk for convenience of the analysis. Okay, and then we have to go to the next order to obtain another equation, which we can integrate over this cell omega to end up with a diffusion equation with the effect diffusivity tensor relying on the Jacobian of this vector gamma. So gamma is very important because it basically determines the effective diffusivity. And so for the kind of arrays that we are looking at, which have a fourfold symmetry, one can show that the effective diffusivity is isotropic. So it can be written as a multiple of the identity, with this being the effective diffusivity, a scalar now. And it can be shown that the effective diffusivity is less than 1. This is not so obvious at first because you put obstacles, and these obstacles occupy some area, so that enhances dispersion because the scalar doesn't have to go very far, doesn't have to discover so much of the area to disperse. But at the same time, you have a reduction of the scalar flux on the obstacles, and this leads to the inhibition of basically the dispersion. So the second mechanism wins, and that's why the effect, and it turns out that the effective diffusivity is less than 1 always. Okay, and so as I mentioned before, there are some sort of explicit asymptotic results for this, and Rayleigh in the 19th century obtained a sort of correction to the effective diffusivity in the presence of very small obstacles, which varies linearly with the solid area fraction, so the area occupied by the obstacles divided by the total area available, by the total area. And this kind of result is insensitive on the type of periodic array considered and whether it's random or not. And this is just a graph showing the linear dependence, these theoretical results in dashed lines against some numerics obtained for hexagonal and square lattices. And of course, you see that over here, this expression is very good, but over here, it's not good. This is when you reach the maximum area fraction. And this parabolic sort of profile that you see over here has been explained by Keller in the 1960s. So what does the Keller result use? Well, it supposes that away from the narrow gap, so this is the dense limit, right? So when we are reaching towards the sort of maximum solid area fraction, what does he say? He says that away from the gaps, so inside the voids in between those obstacles, the concentration is nearly uniform, so well mixed. And all the action takes place in between the narrow gaps between the obstacles. And further on, that basically the gradients of the concentration is unidirectional and uniform across the gap. And so the total flux has this kind of form. And as the gap closes, the sort of profile of the gap has this parabolic shape that can be used to take this underneath, integrate the equation, and get the concentration difference between one void over here and one void over there. In terms of this inverse tan, and we can take the limits from infinity to minus infinity because the integral converges, and end up with this nice expression relating the concentration difference between this bit of the domain and this bit of the domain with the gap width and the area of the void, let's say. Okay, and this is just expressed in terms of the solid area fraction. Okay, so these are the sort of standard results obtained a long time ago. So now I'm just going to talk a little bit more about the large deviation description of the same problem. So in a sense, what is happening is we're taking a different rescaling to obtain the macroscopic coordinates that are rescaled in the same manner. So this is the advective rescaling, which leads to x over t being now order 1. So you want to get an accurate description of the situation at scales x is equal to order t, rather than t to the 1/2, which is what effective diffusion allows you to obtain. Okay, so then you end up with this diffusion equation with a small diffusivity in the beginning, and sort of this singular look of a problem then inspires a WKB approximation, which is multi-scale. So again, you have two scales, one large scale, one small scale, but now you have this sort of WKB sort of representation. And again, you can look to expand the amplitude here in a power series expansion in terms of delta, and you get at leading order a cell problem, an eigenvalue cell problem. The operators here are only depending on the microscale variables y, right? And then you can say that basically here you can see that it's an eigenvalue problem, and the principal eigenvalue here is dependent on this grad x of g, the big G that appears in the exponential. Okay, so then you can do significant manipulations to obtain that actually the leading order amplitude has this form here. This is in 2 dimensions, and the more general form is d over 2. And so there's no dependence on x at all. Okay, and then, yeah, you get that. Okay, so then if you make a change of variables and let q being the grad x of this big G, then you can tidy up the problem a bit. So this is the eigenvalue cell problem because it does take place in this cell domain. And then use the Hopflux theorem, you can see that the big G may be expressed as t times this little g, which is the rate function that appears in the large deviation form I gave. So this is not something actually we've written in a paper, but I just always have trouble in justifying the form of this large deviation in the context of multi-scale phenomena, and that's why I've shown this here. And again, the Hopf-Flachs theorem implies that F and G are Legendre duals. So F here, which is the eigenvalue, and we're interested in the principal eigenvalue, is a Legendre dual of G, the rate function in the exponential, which is what we want. So we want the principal eigenvalue, Legendre transform it to get this rate function, which will tell us how the envelope of the solution evolves, is. And this is, of course, is simplified to assume that the origin is the location of the initial scalar release, and that the scalar is released at time is equal to 0. Okay, so this is the kind of, if we put all this together, this is the kind of rescaled concentration we get here. Oh, there shouldn't be a T here. And again, as I said, the important bit that captures what we need is this rate function G. This bit here, the phi, captures what happens within a cell, so the inhomogeneity that happens within a periodic cell. So if we take now, if we expand using Taylor's G for small x over t, then we can recover the Gaussian approximation. So we get something like 1/4 kappa effective to the -1 x squared over t squared, which once multiplied by t, then recovers the usual Gaussian that you are familiar with. So of course, to get this G, you have to solve this eigenvalue problem, and you have to solve it for a variety of Q to obtain F that are dense enough so that you can Legendre transform F to obtain G. And this is the numerical calculation for G. Explicit results, is more difficult to obtain. There is a useful bound that was obtained by Berestiki et al., which in 2005, which is very simple actually. You just bombard the equation with phi over here, and then you do integration by parts using the periodic boundary conditions and the boundary conditions on the obstacles to obtain that G is bounded below by 1/4 x squared over t squared. And this sort of expression here is basically what you get without any obstacles at all. So this kind of extends what I mentioned earlier, that kappa effective is less than 1 in the presence of obstacles. This tells you that dispersion is always hindered by the presence of obstacles, because the envelope of the solution in the absence of obstacles is let me think. Yes, so without obstacles, you are, let's say, like that, and with the obstacles, you are more contained. Okay, so because this is G is bigger than the G, if you like, in the absence of obstacles, but then the actual solution has a minus here, and so everything is reversed. So as I said, you can calculate G. G is the object of desire here. You can calculate it using finite elements, and we have done this here for the particular case of a square lattice with circular obstacles. But of course, you can do anything you like. It's a simpler problem. It's a cell eigenvalue problem, much simpler than the full problem, right? And we have done this calculation now for 3 representative cases: one for the dilute sort of array where the obstacles are small, one for a dense case where the obstacles are large, nearly touching, and one for an intermediate case, just when the radius is in between, is basically the radius is half the size of the cell side. And this now shows a plot of G as a function of psi, where psi is x over t and eta, right? And the black contours show representative values of G, and the white contours show the effective diffusion approximation. So in the case of G, it's just a quadratic approximation. And what one sees is, in the dilute case, the quadratic approximation corresponding to the effective diffusion approximation is basically excellent, not just in the vicinity of the origin where psi or x over t is small, yeah. No, it's just Xi is X over T, basically. So it's the macroscopic components. Well, Xi is a vector, sorry, and Xi, and so you have X. And, yes, that's right. Yes, thank you. Okay, so yeah, so we expect that the rate function and the quadratic approximation are agreeing near the origin, because at that point the two should be the same as mentioned in the previous slide. However, we don't expect the two to be the same away from the origin. So when X over T is order 1, which is the large deviation regime, we expect some discrepancy. So this is not seen in the dilute case. So the approximation is excellent even in the large deviation regime. But over here, though, however, you do see a large discrepancy. So over here, and in particular over here, you see a large discrepancy, right? So in particular, so this is G sort of plotted in the first quadrant, but you have to sort of complete it in the full domain using symmetry, right? So these become circles eventually, and these lines here become almost like something like that, right? Like a rhombus if you complete it. Anyhow, so in this case, when you have obstacles nearly touching, the rate function is very different to the quadratic approximation that effective diffusivity gives. So it breaks down, if you like, at these distances when X is equal to order T. So Xi is equal to order 1, which is this domain here, where the disagreement is not great. The agreement is not great. Basically corresponds to X is equal to order T, which is the large deviation regime. And this is also shown more, the discrepancy between the two approximations is shown here. So this is the normalized concentration obtained at consecutive times for radius of obstacles nearly touching, and even more so close to the even more dense setup, so even more nearly touching. The maximum, the domain is the maximum value that when they touch A is equal to pi. Okay, so it's nearly touching and even less, even more so. And what you see is that the tail concentrations are much fatter than predicted by the effective diffusion approximation. So over here, the effective diffusion approximation and the large deviation approximation are exactly the same, but the tails over here are different, and the difference is more pronounced at early times. So at late times, basically T is so large that the tails you cannot see. So it's more the early times where a difference between the effective diffusion and large deviation approximations is more is pronounced. And of course, as the obstacles become bigger, then this discrepancy, this disagreement is more pronounced. Okay, so yeah.
If you take into account there are more particles that make it out further than you expect them.
Yes, that's right. Exactly. So the tail concentration are much fatter. So yes. So if it's bad because if you have something toxic, let's say, effect diffusion will tell you, okay, reassure you that the concentrations are lower than you thought they would be at a certain distance.
Or enormous, because that's it in its phone. Right?
Yeah. Yes, that's right. Yes.
It could be very, very large, orders of magnitude different than actual concentration.
Yes, that's right. Yes, they're quite big. And the thing that is quite interesting is that, that it's at early times that you are able to capture more. It's more important, the large deviations. It's not just the large distances, it's also early times where this becomes important. So it gets more of the behavior at early times. Okay, so the last bit of the talk is all about basically some asymptotic results that explain the good agreement between large deviations and effective diffusion approximation in the dilute limit, and sort of give an asymptotic result in the case of the dense limit, where you got this anisotropic sort of behavior for the patch. So instead of having these circular patches, which are the ones that you would expect from effective diffusion approximation, you get this a scalar patch. This translates to a contours of concentration, if you like, that are highly anisotropic. And the aim is to kind of explain why this agreement between the effective diffusion approximation and large deviation is so good in the dilute limit, and also capture a lot better than this effective diffusion approximation the contours of the numerical solution obtained here. Okay, and so it's more convenient to work with a different variable psi that is related to phi, the one in the cell problem, in the eigenvalue problem, by an exponential. And in this case, it's the problem becomes the modified Helmholtz equation described here, but instead of psi being periodic, we have that psi exponential of q dot x being periodic. 2 pi again is this is the choice of our domain. This is the periodicity of the cell that we have chosen, with Neumann boundary conditions on the surface of the obstacles. Okay, and one can then work with matched asymptotics. In the dilute limit, you consider a sort of outer region away from the obstacle, whose solution at leading order is just a mere exponential, so the kind of solution that you would obtain in the absence of any obstacles. And then you can have like an inner region, a boundary layer region obtained by rescaling R with the radius of the obstacle. And then by matching with this outer condition, one can obtain this expression here. And basically the effect of the obstacle is represented by this r to the -1 term. So it has a small effect, this boundary, the fact that you have a small obstacle there has a small effect on the leading order solution for psi. And then one can multiply this equation with exponential of q dot y and integrate and use this and this to sort of, without having to go to higher orders, which it can be quite messy, including logarithmic corrections in A. You have some nice sort of, this is a little trick that gives you the correction to f, the principal eigenvalue that you're interested in, as a quadratic function of q squared with coefficient, the effective diffusion coefficient of Maxwell and Rayleigh, the classical one. And then taking a Legendre transform, you get this quadratic form, the quadratic form for G, which is what again you would have expected from homogenization theory and the effect diffusion approximation, only that this analysis is now done for larger distances from the origin, so in the large deviation regime when x is equal to order t, rather than t to the 1/2. Okay, so this explains why the numerical results were always very well described by the effective diffusion approximation in the dilute case. In the dense case, one can push a little bit Keller's model and Keller's model for the flux to build a discrete network model. So one can take the diffusion equation and then integrate it over this cell omega, and then assuming that in the area occupied in the void between the obstacles, let's say the concentration is nearly constant, then you can end up with this expression here, this sort of equation here that describes the evolution of the concentration in this void, assuming that this is well mixed, in this fashion here. So basically, with alpha being obtained by being basically the constant related to the total flux divided by the difference between the two concentration, the two voids that Keller obtained. And so basically you integrate over, you know, a particular cell, a cell that is, let's say, centered like that, then you assume that the concentration inside this area is nearly constant, and then you find that this integral has, the evolution of the concentration here has to be equal to the fluxes on this, to the 4 fluxes over here, and the 4 fluxes were given by Keller. So this is in effect replaced by a network model with these vertices here corresponding to the concentration in these voids, and this bit here, which look like resistors, corresponding to the edges of your sorry, these edges here correspond to the area, the gaps between the obstacles. And what can work with this equation and sort of obtain a large deviation solution for this, so look for the large deviation rate function associated to this equation. And surprisingly, you end up with an actually explicit expression for the rate function G in terms of some complicated expression that involves the hyperbolic sign, etc. But anyways, it was quite peculiar that we ended up with an explicit expression for this. Of course, it's a very much simpler problem. It's just a network model. There is no spatial variable anymore, but still, it was surprising to get an explicit expression. And how does this expression fare? How does the resulting expression for G fare against the full numerical solution for G? Well, the full numerical solution is here obtained. Again, we look at 2 cases, one where the radius is pi minus 0.01, so the gap is 0.01, and one with a smaller gap, 0.001. And the solid lines correspond to numerical results. The black one along the diagonal, the blue one along the horizontal. So this is G obtained along these 2 directions. The dashed line corresponds to the quadratic approximation corresponding to the effective diffusive approximation. And these dashed dotted lines correspond to the rate function obtained using this simplified discrete network model. And of course, this is a lot better, and even more so as the gap decreases here. But it doesn't go all the way. So the improvement is limited, although it is instructive to work with that model. And I guess it breaks down over here because we have assumed that the concentration in between these obstacles, so over here, is constant, so well mixed, which is not the case. It's not necessarily the case. Okay, so how do we go about to get a more full description of that? So this is just really for people who like asymptotics. Basically, it's again a matched asymptotic treatment. You have 2 regions, the inner gap regions over here, where you scale things this way, and the leading order solution again has an inverse tan sort of expression, just like you had with Keller, but with Keller's version, but now you keep the dependence on X. And you have these 2 constants over here, and similar expressions for the psi, which is the eigenfunction that you're interested in solving, in finding solution, in the 4 sort of gaps over here. And then you use this tilted periodicity to remember psi was not purely periodic, it was related to phi via an exponential. And so you get these extra conditions relating 2 sets of constants with another 2 set of constants. And then you have an outer region, and the outer region basically is defined by a domain where the obstacles are touching. And in this case, again, you have that sort of total flux, if you like, kind of, it's like a flux equation that is conserved. And you find that the outer solution has a limiting form as you approach these singular cusps that is inversely proportional to X, so the distance from the center of of this, from the edge of the cusp, if you like. And similarly, for the other three cusps, right? The psi0 is obtained by, psi0 has this inverse in x power here, and then you have to rotate the solution to get the limiting form in the other three gaps. And again, this involves two constants, which we would need to match with the inner solution in order to obtain our f. But what is key now is to work with this, write the solution of psi0 in terms of the solution to a canonical problem. The canonical problem is as follows. You consider this equation here. So Laplacian is equal to f psi star being the solution to the canonical problem. And you force with particular conditions at one of the cusps and 0 in the other three cusps. So these are sort of the conditions as you approach the end of the domain over here. And you give f, and you want to get the constants associated to psi star as you approach the four cusps. So again, because this is x squared times the x psi star is 1 as you approach here, you end up with a limiting solution that goes like the inverse powers of x plus a constant. And over here with just a constant, because there is no flux assumed in the other bits of the domain. And so you give f to this problem numerically, you can solve it, and it gives you the constants d1, d2, d3, d4. And these constants are the key to make that matching possible. So then you write psi0 as a linear combination of this solution to this psi star with some constants over here that need to be determined by matching with the inner solution. And so you end up with a linear system, 12 equations, 12 unknowns, which you need to sort of massage a little bit, and then end up with a transcendental equation that gives you f as a function of q, which is what you need. So the advantage of this canonical problem is that you solve it once and for all. You don't have to, the eigenvalue problem that was the initial problem that we were looking at, for each gap you have to, for each sort of obstacle size, you have to solve it, right? But here you do it once and for all for this particular asteroid. You solve it in this particular asteroid sort of domain, and you get a table of values, and then you can just use it to get your f of q for all these obstacle sizes in the dense limit, of course. Okay, so how does this fare? Well, this is the same picture I showed initially. The rate function as a function of these macro scale parameters, so x over t, y over t, if you like. And the black contours selected values of g shown. And the red contours is the numerical, is the asymptotic solution, which is very good already. It captures the anisotropicity of the scalar patch. This is essentially what it is if you complete it, and becomes better as the radius of the obstacle increases, so the obstacles are nearly touching. Is this? Yeah. Okay, and so this is again the same figure as I showed before, so just showing what contrasting G against the asymptotic. So this is the discrete network approximation, which assumed that things are well mixed in the area, in the void in between the obstacles, which breaks down for large psi, but it's good over here. And then there's the sort of improvement to this by the asymptotics involving this canonical problem, for which the agreement is very good for large values of a large range of values of psi, and even better again as the asymptotic limit is as we go closer to the asymptotic limit, so the obstacles become bigger. Okay, so, and of course with the cover one can show that the sort of more complex asymptotic solution that we obtain does encompass the discrete network approximation as a limit, so the two collapse, so the thin solid lines agree with the dashed dot lines over here. And of course, all the analysis here will break down at some point, and this is when we go, when f, the principal eigenvalue, or g, becomes much larger than 1. We have assumed here that these are order 1 in the very, very, very tails, which is of course not very interesting, but maybe more mathematically interesting, in which case the rate function is determined by action minimizing trajectories corresponding to the shortest path to go somewhere, okay? So, and this is sort of responsible for the very anisotropic shape of the scalar parts that you see at the very, for very large values of psi. So this is something that, yeah, so we go to a different regime, basically where a single trajectory determines the rate function in this case. So it's not about doing much asymptotics at this point. Okay, so just before the conclusions, I just wanted to mention a similar phenomena that was obtained here for a much simple setup. This is a network, a Manhattan network. So imagine you are in the streets of Manhattan and you can only go either horizontally or vertically. Again, it's a much simpler problem because you can sort of approximate it by a network of one-dimensional edges where diffusion and advection can take place, so things, more exact results can take place. And here we have some Monte Carlo simulations showing the concentration of how it evolves in early times and later times. And at early times, together with the large deviation approximation that is shown in the areas where you're not allowed to go, so in the building blocks of Manhattan, let's say. So the actual Monte Carlo approximations only are allowed to go on the network, and then on the area in between, it's just to show the agreement between the large deviation and the Monte Carlo. You see that it's very close. Anyhow, the important bit here is that you see again this sort of anisotropic scalar patch. This is the example here of a concentration evolving in the absence of any flow. There is some flow here. I'm not going to discuss this bit, but this is just pure diffusion in a network. And you have this sort of rhombus shape, similar to the one we obtain in the presence of this obstacles that we have been talking so far. And what you find is that this bit here, this rhombus shape in this bit here, is explained by a rate function that has this dependence on the L1 norm of psi or x over t, which translates to a concentration that again diffuses instead of in x in L2, in x in L1, or otherwise it diffuses in a different distance than we are used to. It's the so-called Manhattan distance, where you're only allowed to go right, up, right, okay. And again, large deviation results are more visible at early times, and by when the times are large, here are long, then homogenization regime is the one that you can truly only see, because everything else is large deviation affects very, very small concentrations, which are very difficult to obtain numerically. Okay, so I've talked about large deviations as a way to generalize scalar dispersion in arrays of obstacles. The effect diffusion approximation was found to underestimate the concentrations at large distances or short times from the point and time of release. And the effect is strongest in the dense limit when obstacles are nearly touching. In the dilute case, there is no effect at all. So the explicit results capture this non-trivial anisotropic shape of the scalar patch, so this rhomboidal sort of patch that you saw also in the last geometry. And the results are relevant in applications when you are worried about low concentrations, but also if you have reactions. So let's say if you have KDP reactions, then the rate function actually determines the speed of spreading of the reactions. So they assume a macroscopic significance, although they are sort of developed to capture low concentrations for dispersion. Once you switch on reactions, then you get a speed that depends on this rate function. So future directions, I guess there are many. The most simple ones is to consider different geometries, look at the three-dimensional case of spheres, insert a flow, and also the more tricky bit is to sort of understand the random distribution of obstacles. It would be lovely to have experimental evidence of that. I don't know if it's possible. Okay, so with that, I would like to thank you for your attention and look forward to some questions.
Okay, so thank you very much. Are there questions?
Thank you for this interesting talk. So I had a question concerning the possibility of considering the Langevin equation instead of pure diffusion, because usually in applications, molecular diffusion is coming from the overdamped limit of some Langevin.
Yes.
And I was wondering whether you have some intuition or if you know some results on the fact that you get the same rate function by taking the overdamped limit only after the large time limit. You see what I mean?
But you mean the stochastic version of this problem?
Yes, exactly.
Ah, yeah, it's exactly equivalent. I presented it in terms of PDs here, but it's actually exactly
now
equivalent.
assume that you start from the Langevin equation.
Yes, yes, you get exactly the same.
Not diffusion, but Langevin with velocity and position.
Ah, well, it depends on your velocity, I suppose. I mean, here we have looked at the case without velocity, but of course you could put inside a velocity, right? That is obtained by a Stokes flow that is generated via some constant pressure difference, right? And you could add this, and then your eigenvalue problem would have this additional effect that you can do numerically, and you would be able to get the rate function fine. Then the problem. Do
you think you will get the same rate function?
Yeah, you get a different rate function, but you have the methodology to do so. Yes, you have the methodology to obtain a rate function, but of course the presence of a flow will affect the rate function. It's not going to be, exactly the same. Now, a question is whether you can get nice asymptotic results, in these limits. But yes, of course, you can. In general, you can definitely capture tails by solving numerically your eigenvalue problem for sure.
Okay, thank you. Are there other questions?
But speaking of flow, I mean, I guess the simplest thing to try would be a cellular flow. Have you tried doing the homogenization problem? It's a very standard problem, right? The homogenization for a cellular flow.
But with the obstacles, you mean?
No obstacles, right? You just put a cellular flow, but you do the scaling differently, right? You do your large deviation scaling instead.
Yes, but that was what was done by Peter Haynes and Jacques Van Neste, right? Yes, that's what they did originally. So Peter Haynes and Jacques Van Neste looked at dispersion in shear flows and cellular flows.
Okay.
I mean, it's more general, periodic flows, let's say, but then they obtain asymptotic results in shear flows and cellular flows. And then here we just do the obstacle version of that.
Other questions? Okay, I have a small question. How, like, kind of the shape of these obstacles, like the array? So you showed in the end that if you get like the one norm, like the Manhattan path of these obstacles, you get like this anisotropic shape, which is kind of rhomboid, which is.
Yeah.
So how this the shape